Everyone, welcome to my YouTube channel. In today's video, we will discuss about the Parity operation in quantum mechanics. The concept of Parity operation in quantum mechanics. First, we will define Parity operator, and then we will talk about the properties of Parity operator one by one. First, if you want to understand the concept of Parity operator in real life, we can take an example by the reflection of light by a plane mirror. We can take an example, reflection of light on a plane mirror. Suppose you have a plane mirror. If you are standing in front of the plane mirror, you can see that your left side appears as right and your right side appears as left. Like that operation, like similar operation, we can see that when we are dealing with mathematical functions, that operations we call parity operations. So parity operation is nothing but mathematical operators, and it is denoted by the symbol by. So parity operator, it is divided like this. For example, if we have a function of x, and if you apply that function of x by parity operator, you can see that the sign of the input of that function will change. Suppose you have a wave function. In quantum mechanics, we use a wave function. Suppose you have a wave function. So if you apply that wave function by a parity operator, you can see that the sign of the input of that wave function will change. For example, I have this wave function psi x. If I multiply this wave function, if I apply this wave function by this operator by, you can see that the sign of the input of this wave function is changed and it became minus x. So usually, if you have a wave function and if you operate by a parity operator, the sign of the input of that wave function will change. For example, suppose you have psi of minus x, and if I apply this psi of minus x by a parity operator, it will become psi of x. It means parity operator usually changes the sign of the inputs. So this is the definition of parity operator. Parity operator is nothing but mathematical operator, and it's denoted by the symbol by. So when we are talking about properties of parity operator has a different properties. So one of the properties of parity operator is a linear operator. We know about linear operator, so we know the condition of linear operator. So when we are talking about linear operator, or when we are dealing with, or when we are talking about the linear operator, we know that, for example, we have a two functions. The sum of two functions is psi1 plus psi2. So if we apply these two, the sum of these two functions by operator A, it must be equal to A psi1 plus A psi2. So if it satisfies this condition, we can say that this operator is a linear operator. So we will use this condition to prove that parity operator is a linear operator. So let us take an example. A wave function. Suppose you have this wave function, psi of x, this wave function, and you apply a parity operator by. So what will you get? You will get psi of minus x. Psi of minus x. Okay, let us analyze this equation. So psi of x, suppose psi of x is equal to psi 1 x plus psi 2 x. And you have already by which is parity operator. You have a pi which is parity operator. It's equal to, similarly, this psi minus x is equal to psi 1 minus x plus psi 2 minus x. Psi 2 minus x. So, in this part, psi 1 minus x is equal to, according to the definition of parity operator, look here, we know that if you have psi minus x, it's equal to by psi x. So if you have psi 1 minus x, it's equal to psi 1 by psi 1x. Similarly, if you have psi 2 minus x, it's equal to pi psi 2x. By psi 2x. So now what we get? Here we have pi times psi 1x plus psi 2x. We have this. So if we look at this expression, we can see that it satisfies the condition of linear operator. So we can say that this operator is a linear operator. This operator is a linear operator. Therefore, we conclude that by operator or Parity operator is a linear operator. So this is one of the properties of Parity operator. So let us talk about the second property. Parity operator is a Hermitian operator. Parity operator is a Hermitian operator. So let us prove how Parity operator can become Hermitian operator. Suppose you have two functions, psi by psi and phi. You have these two functions. The scalar product of these two functions can be written as by psi comma phi, which is equal to integral minus infinity up to positive infinity complex conjugate of psi minus x pi x dx. This is the scalar product of these two functions. So when we apply the Parity operator by the function psi, so what will happen if we apply the Parity operator by the function phi? The scalar product of these two functions will become psi comma by phi is equal to integral minus infinity up to positive infinity complex conjugate of pi x psi minus x dx. So this is equation number 1 and this is equation number 2. So these two equations, if you look, you will see that here we have minus x and here we have minus x. Why? According to the definition of Parity operator, you know that if you apply a function, if you apply Parity operator by a function, you will automatically see that the sign of the input of that function will change. So since the first equation we are applying Parity operator by the function psi, so the input of that function must be changed. Similarly, the second equation we are applying the Parity operator by the function phi, so the input of that, the sign of the input of that function must be changed. So that's why we give negative. So to prove that the Parity operator is Hermitian operator, we will take the first equation and we will analyze. So let us see how. The first equation we have by psi comma phi is equal to integral negative infinity to positive infinity psi complex conjugate of psi minus x pi x dx. So what we will do, let's x prime is equal to minus x, or we can say that x is equal to minus x prime if we divide the negative sign by both parts of the equation. So let us differentiate this one. If we differentiate, we will get dx prime is equal to minus dx, or we can say that dx is equal to minus dx prime. So here we have variables, which is x prime is equal to minus x is equal to minus x prime, and dx is equal to minus dx prime. So we will change it, these variables, into equation number 1. So what we will get? Okay, in equation number 1, we have by psi comma phi is equal to integral. When we are changing the variable of that function, of that equation, the limit of the integral will change. It will become positive infinity up to negative infinity. So here we have psi complex conjugate of minus x. Minus x is equal to x prime. We will change into x prime. See, minus x is equal to x prime. So phi, here we have minus x prime. Since x is equal to minus x prime. So the position of x we will change minus x prime. Here we are having dx. So now we will change minus dx, since dx is equal to minus dx. So put this minus sign, this negative sign back. So if we put this negative sign here, automatically the limit of this integral will change. It will become negative infinity up to positive infinity psi complex conjugate of x prime phi minus x prime dx. This is by psi comma phi, and we call this we will call this equation number 3. So this is equation number 3. Now what do we want to do? We will compare equation number 2 and equation number 3 to prove that Parity operator is Hermitian operator. So let us compare these two equations. First, write equation number 2. Equation number 2 was psi comma by phi is equal to integral minus infinity up to positive infinity psi complex conjugate x phi minus x dx. This is equation number 2. And equation number 3 we have by psi comma phi is equal to integral minus infinity up to positive infinity complex conjugate of psi x prime phi minus x prime dx. This is equation number 3. If we look at these two equations, what we will get? We will get that these two equations are equal. This part of this equation and this part of this equation are equal. You can see here psi of x, and you can see here psi of x. Don't look at x and x prime. X and x prime are variables. We will look at only the sign. Here is positive x, here is positive x. Here negative x, negative x. Dx, dx. See. Now we can conclude here psi comma by phi is equal to by psi comma phi. This is the condition of Hermitian operator. This is the condition of Hermitian operator. So we can say that by operator is a Hermitian operator, or we can say that the Parity operator is Hermitian operator. Thank you so much.